Hey guys, welcome back to my YouTube channel. So as we discussed, we have completed everything on a semiconductor physics basics. So now we are covering some miscellaneous topics. So here let's see how the interaction of light with semiconductor is when there is interaction of light with semiconductor, how the things like how the magnetic charge carrier and how the magnetic charge carriers are varying. So those things let's come into picture. Let's understand those things. So here you see this is the light falling in the semiconductor physics at x is equal to 0 versus the length of the semiconductor device. So this point, this interaction is I0. So I0 is the intensity of light at x is equal to 0, and this graph which is equal to I of x. So this is intensity of light at any point of time. So that is pointed as I naught e power minus alpha x. Okay, so this is simple exponential decaying, right? So the alpha they are terming as the absorption coefficient. So this is absorption coefficient. So absorption coefficient Cm per minus 1. So this will depends upon wavelength of light and the wavelength of material. So it will depends on both the thing. So it depends on material and wavelength. So it will wavelength of light and material. Based upon these things, it will vary. Depends on material. Okay. So this is one of the thing. So based upon the light interaction. So this is how the graph of term that we can represent it. So this is normal, just a quite of incident. But in the semiconductor physics, we have a separate session for understanding the minority charge carrier injection. So they will intentionally inject some kind of charge carrier so that to find out the behavior. So this is natural phenomena. So based upon this thing, how the things will vary. So in solar panel we see, right? So how the light interaction is changing the thing. So similar to that. So another one key term there is that is injection. So in the lab they will inject some minority charge carrier into the semiconductor and then they will observe the behavior. So that thing we are going to find here. So the injection of minority charge carrier that we are doing, it's not a natural process we are doing. So minority carrier diffusion. So how the carrier concentration which is generated will diffuse from the different location. So because there is some instability, some non-equilibrium will be created, right? So that thing we are going to see. So two things how that is done is, one is optical illusion, optical injection, not illusion, optical injection. So they will inject charge carriers with optical injection. So this may not be doing more many times, but there is electrical injection. So this will is our area of interest in EC department. So electrical injection. Okay. So even we can directly say this is PN junction diode in forward bias. The application is same. So PN junction diode which is acting in forward, right? So where we are injecting the charge carriers. It's not minority charge carrier only. Both charge carrier we are injecting. The injection is happening because of external supply. So we can even state that as a externally we are doing some kind of injection. So okay. So that is not a natural process, right? So we are doing some kind of injection. So this will be very important to analyze. So that is what we will be studying in the PN junction diode completely. So here let's go through glance like how it will work under those things. So let me draw a diagram to for make you guys to understand here. So you can clearly state that this will be semiconductor physics. So semiconductor device at x is equal to 0 and at as a direction x pros. Okay. So there will be two level. So which will be the n0 which is nothing but the p n type, and this is the charge level carrier for the p. So let's take this as a n type. So we know that in n type the n charge carrier will be more. So that is we are representing as nn0. But minority charge carrier will be there but is low. So it will also be equal to ni squared divided by nn0. This we already studied with mass action law. Okay. So whenever there is an injection or optical illusion, there is a charge carrier or photoelectric effect that is happening, there will be quite increase in extra electron concentration. Not only for a majority charge carrier, both minority charge carrier as well as minority charge carrier. That will happen. So this net change, right? So this is because of the external operation that we have done. So that is what we are going to analyze in the series of lecture. So whenever the h nu in the incident energy level is greater than the energy gap, which is light or photon is operable, then the light is capable of then the incident light is capable in breaking the bond, and which will be making more electrical electrons or whichever thing that is available for the conduction process, capable of breaking covalent bond. Okay, covalent bond. So I hope it is understood. So in the next lecture, in the next thing, let's study deeply. So let's take a region of observation. So let's deep dive into how the charge carrier will work. Okay. So this is minority charge carrier level. So this is the lower level of minority charge carrier. So we will analyze only minority charge carrier in this thing. So I will know why we are analyzing minority charge carrier. So here we are taking PNX, means this is an n-type material. So the subscript will make it as an n-type material, and P is the charge carrier. Okay. So this is the lower thing. Lower order thing means let me do it. So this variation is there, right? This height is P n naught. So which will be the constant level, which will be throughout the semiconductor. Okay. So we can also write this level as the Pn0, which is equal to Ni square divided by Nd. Okay. This is x, and this is x is equal to 0. Okay. So whenever there is photon or light interaction, which is h nu, which is greater than the energy level, okay, which is Ec minus Ev, right? So this is happening. Then what will happen? The extra charge carrier will be produced, and then that will decay slowly into 0, because only at the incident region there will be more charge carrier. As it's go over the semiconductor, it will be vanishing to 0. So that thing we are seeing here. So this net change is there, right? So this net change. So this net change is there, right? So that is what we are seeing here. So which is nothing but Pn not dash. So which is Pn not dash. So this is variation in the normal charge carrier, minority charge carrier. So this graph can be also written as Pnx, which is also equal to Pn naught, which is constant term, and dou P of x. So which will be some varying term. This can be also written as Pn naught plus Pn naught dash e power minus x divided by Lp. This Lp, those things I will come into picture. So for now, let's see the thing. So this graph, this area, the external net change, right? So this is only this one. Okay, that is only our observation. That is only our study. This is an n-type semiconductor where we are focusing only on minority charge carrier. Minority charge carrier. I will know why we are not focusing on majority charge carrier. I will know, and from next lecture I will give you that information. For now, scope with this. So this is an minority charge carrier, minority carrier versus distance across the semiconductor. Okay, so this is how the variation will look like. So here some terminology that I have to name. That this is nothing but thermal equilibrium minority Hole's concentration. This is Hole's concentration or minority charge carrier concentration. Anything is same. Okay, the Pn naught dash, here it is, right? So which is optically generated, minority charge carrier. Minority carrier at x is equal to 0. Okay, so this is thing. This del p of x, this change is, right? So this is the steady state excess minority charge carrier analysis. Steady state excess minority carrier of at any x. Then this one, the LP and those things I will be knowing in. So LP, which is nothing but the diffusion length of holes. So this is some lab parameter that will be given in question if they are asked. So diffusion length of holes based upon the semiconductor material. So diffusion length of holes. Okay. So the Pn of x, here it is here, right? So this is the total holes concentration. Total holes concentration at any x. Okay. So this is for n type. Even we can draw for p type. P type will also be similar to that. Some kind of excess things will be generated there. So any type of charge carrier we can analyze this one. So let me give you the inputs for an p type. How it will be looking here is the, I'm not going to draw a thing that you can take care of it. That is simple, similar to that. So I'm giving you the thing. So n p of x. So p is the type of the material, n is the charge carrier. So here is the minority charge carrier at the p type, which will be equal to Pn naught plus alpha n of x. Alpha or do anything you can state it. So np naught plus np naught dash e power minus x divided by lp. Okay, so this is what the formula will come for the p type minority charge carriers. So which is similar to that. Same, sorry, that is not a lp, that is ln. Okay, so as it is an n type minority charge carrier of n. So that we have to take into our understanding. Sometimes they will even say this as a np naught plus np naught dash e power minus modulus of x, because they sometimes they will reference as a negative, so that's why they will represent sometime as a modulus of x also. So both things, please make a note of it. So this is how the charge carrier will look like. So diffusion length, I have said you one thing, right? So diffusion length, how the diffusion length will vary is that, so diffusion length, if it is an lp, then that will be directly proportional to dou p divided by tau p. So dou p, as we know, that is a diffusion constant. Tau p is the average time, average lifetime. So tau p is the average lifetime of holes. So these are some constant they will be providing. So you guys will not to be worried about those things. So we can state that if L is equal to LP, then the value will be looking like NP naught dash e power minus 1. So it will be equal to 1 by E Pn naught dash. So at the L is equal to LP, then there will be at the state of length thing. The length at which the steady state excess carrier concentration become 1 by E time. So that is what the significance behind it. So when L is equal to LP, the length that is the length at which the steady state carrier concentration will become 1 by E time of the normal minority charge concentration level. So this is not that much difficult. So please, we have to make a note that whenever there is an interaction of light, there will be some extra charge carrier that will be produced. So that we are analyzing here. That in an n type, a minority charge carrier, how that will vary is the, so np naught is the constant thing that is throughout the semiconductor. Because of the light interaction, the delta p of x that is coming into picture. That is dou p of x, or any numerology we can state it. So the dou p of x which is coming extra, that is what we are analyzing here. So I hope this is understood for you guys. So if you guys have any doubt, please ping in the comment section. So like, share and subscribe channel. Stay tuned for the next lectures. Thank you.